All right, good morning, everyone. So let's get started. In the previous class, we were discussing Mrs. Gerber's lemma. I gave a proof of following lemma, which gives a lower bound on the conditional entropy of the output of a BSC conditioned on some shared random variable u. So this U is perhaps available as side information, or yeah. So basically you have U, which is used to generate an X, and X is transmitted across a BSCP. Then the conditional entropy of Y given U is lower bounded by the following quantity over here, which depends only on the conditional entropy of X given U and P. Okay. And in the case where U is independent of X and Y, we have that exactly h of Y is equal to the following quantity. So this inequality becomes an equality when there is no U. So this was for a scalar random variable. Now you can also prove a vector form. So if instead of a single random variable y which depends on u, if you have a sequence yn, so you take a random variable u, use this to generate any random sequence xn. It could be arbitrarily jointly distributed. It's just a binary sequence drawn according to some distribution dependent on u, and you pass this through a BSCP. And in the output, you get yn. So in this case, the conditional entropy of yn given u divided by n is lower bounded by a very similar quantity. Okay, and in this class, we'll prove this, and we'll look at a couple of other inequalities, which will be used to prove converse results later on. And we'll see maybe one application of one of the inequalities in this particular class. So before we proceed, any questions regarding Mrs. Gerber's lemma or what we discussed in the previous classes? All right. Yeah. So these inequalities.
Sir?
Yes.
Sir, here U is also vector is in also vector form, right?
No, U can be any arbitrary random variable.
Okay.
So it need not be binary. It is some discrete random variable which could be drawn from any arbitrary alphabet, and U need not be a vector of length n.
Okay.
So you don't generate xn IID IID according to U or anything.
Is it like a UN is a message vector in coding theory?
In some sense, yes. So we'll see that whenever we're talking about degraded broadcast channels, you'll have a message U. So we'll discuss channels of the form. So you transmit some U, and maybe through some particular channel. Sorry, maybe not U. Let me call it something else. So you transmit some vector xn through a broadcast channel, you will get yn. So this is channel 1. You will get a yn, and then you pass yn through another channel, you get zn. So a degraded broadcast channel is where the transmitter sends an xn. One of the receivers gets yn, whereas the other receiver gets zn. So zn will be a copy which is more noisy than yn. So we'll see channels of this form, and we'll see the interpretation of this for such particular channels. But in general, when we're talking about multi-user information theory, we'll see that as you mentioned, you'll be generating instead of generating code books. So we'll use the U, the random variable U, to sort of randomize the code book. And this U is assumed to be known both to the transmitter and the receiver. So U is not really the message, but U is used as some kind of a random seed to generate the code book. And using this, and this random seed is known both to the transmitter and the receiver, and they'll use this to identify which code book is used for transmission and then decode.
So is it like in classical error correcting codes, what we do is the code book is fixed. So here
Exactly.
the code book is not fixed, but it is varied according to U, the value of
Exactly. So you generate one random U, you pick a random U, and depending on U, you pick one of those code books. Maybe you have 10 code books. You're going to choose one of those code books and then use it for transmission.
Okay.
But it also depends on the message. So for every message, you'll be choosing a different code book. So it's a little more subtle, but at a very high level, that is what is happening.
Okay, fine, sir. Thank you.
So we'll probably see some of this when we actually go to a multi-user problem, and then we'll see this random variable U, which is actually what we call an auxiliary random variable. So unlike the point-to-point case, where the capacity is the maximum of some mutual information, when we go to channels such as broadcast channels, or even when you talk about information theoretic security, the capacity is not just some mutual information between X and Y, or X, Y, and Z, but in fact you'll see that that it's equal to some mutual information conditioned on some other random variable U. But yeah, more about that later. So in fact, we'll see that the U that we'll use, we won't be using a small number of code books. We'll be generating one of an exponentially many code books and using that for transmission. But yeah, so we'll see that in more detail later.
Okay.
Okay. So this was the Mrs. Gerber's lemma. So right now, I mean, some of these results may seem a bit mysterious. It's not apparent as to how this is useful later on. But I promise you, once we get to broadcast channels, we'll be using these tools. But we'll see that a slightly, a similar inequality for continuous random variables, which we call the entropy power inequality. This can be used to, we'd actually apply that to understand something about just the point-to-point additive noise channel. Okay, so but before that, we'll just see a quick proof of the vector form of Mrs. Gerber's lemma. So discussing these results has, there are two motivations for discussing these. One is, of course, we'll be using them to derive converses. But secondly, it's also a good exercise in trying to understand how the various inequalities that you've already studied, such as data processing inequality or Farnose inequality or the chain rules of mutual information, are actually used to prove many of these interesting results. And these results are used in a wide variety of problems. So we'll do a quick proof of Mrs. Gerber's lemma, the vector form of Mrs. Gerber's lemma. And so we want to show that if you have this particular problem, so you have a random variable U, and you generate and another random sequence xn, these two can be arbitrarily jointly distributed as long as they're discrete, and xn is binary sequence, it's fine. So you pass xn through a BSCP and you observe yn at the output. And we want to show that the entropy of yn given u divided by n is greater than or equal to this quantity. The binary entropy of h2 inverse of h of xn given u divided by n star Okay, and the proof of this statement basically is by induction. So for n equal to 1, we've already proved it. It is basically the scalar version of Mrs. Gerber's lemma. So to prove the induction step, let us assume that the statement is true for n minus 1. So we know that for all joint distributions between u and xn and for all p, the following holds. H of yn minus 1 given u divided by, or let me use something else. So for every maybe w, h of yn minus 1 by w, given w by n, is always going to be greater than or equal to h2 of h2 inverse of h of x n minus 1 given w by n star p. Okay, so we'll assume that this is true. Okay, and we'll use this, and we want to basically use this to prove this statement, the statement for n, xn, xn and yn. Okay, so we'll start with the right hand side of the inequality. Okay, so on the right hand side we have h2 of h2 inverse of h of xn given u by n star p. Okay, so I'll split h of xn given u by n in the following manner. So h of xn given u is h of xn minus 1 given u plus h of xn given xn minus 1 u. So I claim that this quantity is h of xn given u. So what property have I used to split this?
Chain rule.
Right. So I've just used chain rule of entropy. Right. All right. So given this, I'm going to write it in a more convenient form. So I'll write h of x minus 1 given u divided by n as n minus 1 by n into h of xn minus 1 given u by n minus 1. I'm just multiplying and dividing this by n minus 1. Okay. Now there's a very specific reason I'm trying to do this, because ultimately I want to bring this down to n minus 1. So this is one quantity that I'm interested in, and I know that I can handle using my induction step. But now there's this residual quantity as well, and I want to know how to handle this particular term. So I'll bring it to this form. So I know h of xn minus 1 given u by n minus 1, right? So here this should have been n minus 1. Okay. Now I claim that, so I have this particular quantity over here. So I have h2 of h2 inverse of n minus 1 by n into h of xn minus 1 given u by n minus 1 plus 1 over n times h of xn given xn minus 1 u star p. Okay, so if I call this particular quantity alpha, then this quantity is 1 minus alpha. Do you agree? Because n minus 1 by n plus 1 by n is equal to 1. Okay, so basically I've written it in this fashion because now this sum is a convex combination of this term and this term. Right, so I'm writing this as a convex combination. And I claim that this is less than or equal to n minus 1 by n of h2 of h2 inverse of h x n minus 1 given u by n minus 1 star p plus 1 over n times h2 of h2 inverse of h of xn given xn minus 1 u star p. So basically I take this out. So it is this quantity plus 1 over n times this function of this quantity. Okay, and why can I say this? So what property am I using to prove, to get this particular step?
Property of convex function.
Correct. So in the last class we showed that h2 of h2 inverse of v star p, so this is convex. It's a convex function of v. So I have used that property over here. So it's a convex combination of these two. Okay, that's very good. So this term is exactly what we want. So from the induction step, we know that this quantity is less than or equal to h of yn minus 1 given u by n minus 1. That follows because we are assuming that the statement is true for n minus 1. So h of yn minus 1 given w by n is greater than or equal to h2 of h2 inverse of h of xn minus 1 given w by n minus 1 star p. So we are going to use this in this particular step. So this follows by the induction step. And similarly, we are going to use the same thing for the second term as well. So this is going to be less than or equal to h of yn given xn minus 1 u. So this is the w in this case. Right? So this quantity is less than or equal to h of yn y sub n given x superscript n minus 1 u. Okay, so the first term is one of the terms we need to get h of yn given u. Basically, I can cancel these two terms to get this term. But the second term is still not in a form where we can just combine them directly, because I have h of yn given xn minus 1 u. Basically, what I want is h of yn given yn minus 1 u. But I claim that this quantity, h of yn given xn minus 1 u, is equal to h of yn given yn minus 1 and xn minus 1 u. Any thoughts as to why this is true?
Memoryless property.
Exactly. So we're passing this through a memoryless channel. So for any memoryless channel, the mutual given xn minus 1, yn and yn minus 1 are independent of each other. So the mutual information between yn and yn minus 1 given xn minus 1 u. So this is equal to 0. These two are conditionally independent given xn minus 1. And basically just splitting this gives you h of yn given xn minus 1 u minus h of yn given yn minus 1 xn minus 1 u. So this basically follows from the memoryless property. Okay, so now we almost have everything we need. So I'm going to retain the first term as it is, but now I'm going to say that the second term is less than or equal to h of yn given yn minus 1 u. Why is this statement true?
after conditioning?
Exactly. So conditioning can only reduce entropy. So conditioning reduces entropy. So this quantity is less than or equal to this quantity. Now I have everything we need. So just combining this using the chain rule, we get 1 over n of times h of yn given u, which is what we wanted. So we showed that the right hand side is upper bounded by the left hand side. All right. So let's quickly this once again. So we proved the Mrs. Gerber's lemma for n equal to 1, the scalar case. Okay, and we're going to prove for general n, we just use induction. So since we know that this is true for n equal to 1, we'll assume that this statement is true for any general n minus 1, and then all we have to do is prove that this statement is true for n. Okay, so we'll start with the right hand side, and basically the innermost term is expanded using the chain rule of entropy. And once you expand this using the chain rule of entropy, you write this as a convex combination of two terms. Okay, because so far the only things that we know about this particular function is of course by the induction step we know that this is true for n minus 1, and the second thing that we know is that this function is convex. Okay, so we want to use the convexity property. So we decompose this as a convex combination of two terms, and then you just apply convexity, and then it's just a sequence, and after that you identify that for the second term the channel over which you're operating is memoryless, and therefore you can bring in an xn minus 1, and you just use conditioning, the property that conditioning reduces entropy, to get 1 over n times h of yn given u. Right? So hopefully at least each of these steps is separately clear. In general, I mean, knowing when to use which property is not very easy, and it generally comes with experience. That's the only way you know it, and some of these ideas are very nice. So it's not easy to identify how to use a particular property. All right. Okay, so any questions? All right, so this was Mrs. Gerber's lemma for general binary symmetric channels. Now, we're going to give a slightly more general version of this, or we're going to look at a more general problem where now we have the channel is not a BSC, but it's an additive noise channel. So it's a continuous alphabet channel. X belongs to R. You're passing a random variable or a random sequence on R or Rn through a channel where the noise is just added. This sum is the real sum. So you add some noise which we call Z, and at the output of the channel you observe Y, which is also a real quantity. Okay, so we'll assume that X has some density Fx, and the random variable Z has some density Fz, and X and Z are independent of each other. So the entropy power inequality similarly gives a lower bound on the differential entropy of Y, and specifically the statement says the following. So 2 raised to 2 times h of y is greater than or equal to 2 raised to 2 times h of x plus 2 raised to 2 times h of z. And this inequality is an equality if and only if x and z are Gaussian. Okay, so let's now see why why this is called the entropy power inequality, and why this is written in this sort of specific form over here. Okay, so consider suppose that z is Gaussian. Okay, if z is Gaussian with mean 0 and variance sigma square, then what is the differential entropy of z? Does anyone recall?
It is half into log 2 pi e into sigma square.
Yes. So good. So it is half log 2 pi e sigma square. Okay. So if z is Gaussian with any mean, in fact, the mean doesn't necessarily have to be 0. So for any finite mean and variance sigma square, the differential entropy of z will be half log 2 pi e sigma square. Okay, and what happens if you look at 2 raised to 2 times h of z divided by 2 pi e? What is this equal to?
Sigma square.
This will be equal to sigma square. So it is the variance or the power, right? So if it's Gaussian, then 2 raised to 2 times h of z by 2 pi e gives you the power of the random variable, right? And that's precisely why this is called the entropy power inequality. If you divide both sides by 2 pi e, just one second, then basically if these are Gaussian, then this basically says that the variance of the output is greater than or equal to the variance of x plus the variance of z, and in general uh, 2 raised to 2 times h of x by 2 pi e. This is called the entropy power of x. Of x for any continuous random variable x. Okay, there was a question.
So, I was also like asking the same thing. Like the output, then it means like the output power is at least the input power plus the noise power, something like
Yeah, so I mean, if it's Gaussian, then it's actually an equality. The output power has to be equal to the sum of the input power and the noise power, because it's just a statement about variances, right?
Yeah, yeah.
But basically what the entropy power inequality is saying is that the entropy power of the output, note that this is not exactly the variance for a general random variable, 2 raised to 2 times h of y by, or 2 raised to 2 times h of x by 2 pi e is not exactly equal to the variance if it is non-Gaussian.
Yeah.
But this is something that we call the entropy power, and the entropy power inequality says that the entropy power of the output is greater than or equal to the entropy power of the input plus the entropy power of the noise. Okay, and the entropy power inequality has a variety of applications, not just in information theory, but also in probability and statistics. There have been people who have used the entropy power inequality to prove sort of central limit theorems. you can show that. In fact, you can show a different version of the central limit theorem where the sum of IID 0 mean variance 1 random variables converges to a Gaussian. So typically the standard central limit theorem is used to show convergence in convergence in distribution. You can prove a different version of the central limit theorem where you show that the KL divergence between the the distribution or the density of the normalized sum and the density of a Gaussian converges to 0. And the entropy power inequality can be used to show such a statement. Okay, and so it's an interesting problem in its own right in probability and statistics as well. Okay, but now right after this, we'll show an interesting application of the entropy power inequality to show that for any given additive noise channel, the worst channel in some sense is the AWGN channel. I'll make that statement a little more precise. But you can generalize this entropy power inequality over here to slightly other cases as well. One where you can replace h of y by h of yn by n. So if you have then then the entropy power of this vector is defined as 2 raised to 2 times h of yn by n. Right? And you have the entropy power inequality for vectors, and this holds even if you have even if it is conditioned on some random variable u. So more generally, 2 raised to 2 times h of yn given u is greater than or equal to 2 raised to 2 times h of xn given u plus divided by n, this by n plus 2 raised to 2 times h of zn given u divided by n. So all of these statements can be proved. In the interest of time, I will not prove the entropy power inequality. It's a bit complicated, but it's good to be aware that there is such an inequality. So we'll use this once again when we go to Gaussian broadcast channels. But very quickly we'll see an application of this right away, just for point-to-point additive noise channels. If you're interested in the proof, yes.
Sir, like for the entropy power inequality, like it can be used only for like continuous random variable, or it can be applied also for discrete random variable also.
So generally it holds for discrete random variables as well, as long as the addition is over the binary field.
So if
sorry, not the binary field, the real field. Yes.
So if it like holds for discrete random variable also, it seems like 2 to the power 2x, it's actually like very similar to the number of typical sequences in that alphabet, right? From where that x belongs to, right?
Yes.
Like the number of typical sequences actually 2 to the power hx plus or minus epsilon. So
okay.
So like it seems
but note that, so it's generally 2 to the n times h of x, right? That is the size of the typical set, whereas this is something different. So it's 2 raised to h of xn by n.
Okay.
So it's making a different statement. All right. For discrete random variables, there are other sort of inequalities that are known. This is probably the most interesting for continuous random variables rather than discrete random variables, because typically the additive noise is not discrete, it's continuous. Right? Whenever you're talking about discrete random variables, the addition will generally not be over the reals. It will be over some finite field. And in that case, this entropy power inequality does not hold.
Got it.
So there are generalizations of so that is a regime where something like Mrs. Gerber's lemma is used, and there are generalizations of that known for slightly more general alphabets and so on. So as I mentioned, I will not discuss the proof. If you're interested, you can go. There are many different proofs of the entropy power inequality. There are generalizations of the entropy power inequality. And this is one recent paper published in 2007, which gives one proof of. Yeah, so this paper itself has 2-3 different proofs of the entropy power inequality. Okay, so but what we want to do now is show the following statement. So suppose that we have the following problem. So we have an additive noise channel where you transmit Xn, the additive noise is Zn, and you observe the output Yn. So it's a classical additive noise channel. The input has to satisfy a power constraint of P. So the expected power of Xn should be less than or equal to n times P, or the expected or the average energy of Xn should be less than or equal to n times P, and Zi is IID with zero mean and variance sigma square. So those are the only constraints that we are imposing. So the noise is additive. It is IID with zero mean and variance sigma square. So the question is, under these constraints, which distribution actually minimizes the capacity of the channel? And we'll see that in fact it is the additive wide Gaussian noise channel. So the capacity is minimized when Zi is Gaussian. Okay, and that is the reason why we study AWGN channels so extensively. So one reason is, of course, because of the central limit theorem. Whenever you have the AWGN channel is probably the most ubiquitous because of the central limit theorem. If you have many independent components of noise being added together, then it's going to look Gaussian anyway. But also, it's another reason why we look at the AWGN channel is because whenever you have a point-to-point channel with additive noise and you don't have any other information about the noise except the mean and the variance, it's best to assume that it is the worst case noise, and the worst case noise is Gaussian. All right. So we'll see a quick sort of proof or an argument as to why this is true. So one very interesting property about the Gaussian is that among all possible continuous random variables with a given mean and a given variance, the differential entropy is maximized by the Gaussian random variable. Okay, and in fact, you can make such general statements for continuous random variables, for discrete random variables as well. So the general question is the following: if you have a random variable x or a class of random variables x with a certain mean, a certain variance, in fact, you can impose constraints on general kth order moments. So if you have under these constraints, which distribution maximizes the entropy, or which distribution maximizes the differential entropy? And we'll see. And in fact, it turns out that the maximizing distribution always has some sort of an exponential form. So if you have constraints on the first k moments, then the maximizing distribution is going to look like e raised to minus some power of k, e raised to minus x raised to some power of k. Okay, So for a more general for the most general statement and for the proof, you can look at chapter 12 of Core and Thomas, second edition. But let's do a proof of the fact that of a more slightly simpler case. The proof is general and it applies to and you can generalize this to for general moment constraints. But we'll just look at first and second moment constraints and see what happens. Okay. So the question that we want to answer is the following. Look at all possible densities with zero mean and variance sigma square. Now, among these densities, which density maximizes the differential entropy of X? Okay, and what is the maximum differential entropy? The claim is that this is equal to half log 2 pi e sigma square, and it is equal to this if and only if X is Gaussian with zero mean and variance sigma square. Okay. So this statement is hopefully clear.
Yes, sir.
Okay. Yeah. So there are different ways of proving such a statement. For discrete random variables, you can either look at you can pose this maximization as a standard convex optimization problem and use Lagrange multipliers and try to solve it. But for densities, it is slightly more complicated. And the fact that we already know what the solution is can help us get more intuitive as well as maybe not intuitive, but a simpler proof and one which uses purely information theoretic ideas. Okay. So let's look at the proof. So let's start with the entropy of X. Consider any X which has density Fx. The mean of X is equal to 0 and the variance is equal to sigma square. So by definition, this is equal to integral minus infinity to infinity minus f of x log f of x. Okay, so this is just by definition. Now I'm going to play a trick. I am going to multiply and divide this f x of x by the density of a Gaussian with zero mean and variance sigma square. Let me call that g of x. Okay, where g is 1 over root 2 pi sigma square e to the minus x square by 2 sigma square. Okay, so far I have not done anything else, but one of the main reasons why I'm going to do this is because I want to get a KL divergence term. Okay, so I'll split the log, the terms within the log, into 2. So this will be minus infinity to infinity f of x log f of x by g of x plus integral minus infinity to infinity. So it should be minus integral minus infinity to infinity f of x log g of x. Okay. So the first term is something that we all recognize. It is just the KL divergence between fx and g. Okay, and let's look at the second term. Now we have this term which we are not sure how to handle. So let us plug in what g of x is equal to. So this is integral minus infinity to infinity f of x log e to the minus x square by 2 sigma square divided by root 2 pi sigma square dx. Okay, so we have this. Now this h of x is less than or equal to integral minus infinity to infinity f of x log. So the KL divergence is always greater than or equal to 0. So minus the negative of the KL divergence is always less than or equal to 0. Right? Because KL divergence is always greater than or equal to 0. Okay, so now I'm going to split this into two terms. And so it is log e to the minus x square by 2 sigma square minus integral from minus infinity to infinity f of x log 1 over root 2 pi sigma square. Okay, so for the first term I've shown that this term is less than or equal to 0, and the second term I've just split it into 2, just using the property of the log. So it's integral minus infinity to infinity f of x. This is just x square minus x square by 2 sigma square times log e. Okay, and the second term is just minus infinity to infinity f of x log 2 pi sigma square divided by 2. It's log square root of 2 pi sigma square, which is just log 2 pi sigma square by 2. Okay, so what is the first term equal to?
Sir, second moment in content.
Correct. So it's just the second moment, which we know is so it's second moment times something. So log e divided by 2 sigma square times the integral minus infinity to infinity x square f of x, which is just the second moment of x, and that is just sigma square plus what is this term equal to?
That will be only log 2 pi.
Correct. So it will be just log 2 pi sigma square, because integral minus infinity to infinity f of x is equal to 1. Okay, so it is half log 2 pi sigma square. So these two terms cancel, and therefore just adding these two up, you get that this is equal to half log 2 pi e sigma square. And we know that this is the differential entropy of a Gaussian random variable with mean 0 and variance sigma square. Okay, so let's go back. So the only point where we used an inequality was at this point, right? So everywhere else it is an exact equality. The only step where we used as an inequality was here, in saying that the KL divergence between fx and g is always greater than or equal to 0. So when is this an equality?
So when both distributions similar, the curl divergence will be 0.
Exactly. So this is equal to 0 if and only if the KL divergence is equal to 0, and that happens if and only if the two densities are exactly the same. And which implies that equality holds if and only if it is Gaussian. Okay. So among all random variables of the same mean and variance, the distribution which maximizes the differential entropy is the Gaussian. Okay. Any questions? Okay. So let's try to use this for the problem that we're interested in. So what is the worst additive noise channel for a given transmit and noise power? Okay. So basically what we want to know is what is the minimum overall Fz of the capacity, which is the minimum overall Fz, the maximum overall Fx of the mutual information between x and y. Okay, so we can write the mutual information as the difference between the differential entropy of y and the differential entropy of y given x. So this is just h of y minus h of x plus z given x. What can you say about the second term? So what is h of x plus z given x? Correct. So since you already know x and x and z are independent of each other, the entropy or the differential entropy or even the entropy of x plus z would be the same as the entropy or differential entropy of z. Okay, so this is good. So this is, at this point we are going to use the entropy power inequality. So this is going to be greater than or equal to. So we have from the entropy power inequality, we have that 2 raised to 2 times h of y is greater than or equal to 2 raised to 2 times h of x plus 2 raised to 2 times h of z. So h of y is greater than or equal to half log 2 raised to 2 times h of x plus 2 raised to 2 times h of z minus h of z. All right. So we know that the maximum of this overall possible fx is going to be so this is maximized when x is Gaussian, right? So max of Ixy over all possible fx. So this is going to be greater than or equal to half log 2 raised to 2 times h of x, which is going to be p 2 pi e p plus 2 raised to 2 times h of z minus h of z. Okay. So we've seen that this inequality is an equality. So in the entropy power inequality, this is an equality if and only if both x and z are Gaussian. Right? So it's an equality in the entropy power inequality if and only if it's a Gaussian. So this is always going to be greater than or equal to log 2 pi EP plus the entropy power of Z, so 2 pi E sigma square. The second term is also maximized. So this quantity is minimized when h of z, when z is Gaussian, because this is maximized when z is Gaussian. So this is obviously going to be greater than or equal to this minus the differential entropy of a Gaussian, which is half log 2 pi e sigma square. So this is half two pi EP plus 2 pi E sigma square divided by 2 pi E sigma square, which is just half log 1 plus P over sigma square. Right? So the capacity is always going to be greater than or equal to half log 1 plus P over sigma square, and it is minimized. So this becomes an equality if and only if Z is Gaussian.
Sir?
Yes.
Sir, in the second line, like what property are used for AZ? Like minus AZ, it will be like we want to like minimize this one, so that means minus of AZ. That is like we need to maximize AZ so that we have put the Gaussian. And what
Yes.
about the in the bracket thing like
In the bracket, right? Yeah. So I'm glossing over some of the details. So try to look at the function. So whatever, half log alpha plus 2 raised to 2 to the x minus x. Okay, and see whether this is an increasing function or a decreasing function of x.
increase?
It is.
It will be decreasing if we split
Linear.
values. X, it will become
Log alpha plus
Hello, am I audible?
Yes, sir.
Yes, sir.
Okay, yeah.
Log
Sorry, there was a power cut here. Yes, go ahead. Yes.
log alpha plus 2 to the power 2x is
Uh-huh.
an increasing function.
It will be.
It is an increasing function in x.
It's an increasing function in x, yes. But minus x is decreasing in x,
Minus x is decreasing, yeah.
right? So, but also the fact is that this this is a strict inequality. The first term is a strict inequality if z is non-Gaussian.
Okay.
Okay, so here basically I'm using that the entropy power inequality becomes an equality if x and z are Gaussian,
Yeah.
right? So the maximum mutual information is going to be greater than or equal to the quantity which makes it an equality, which is half log, which turns out to be half log 1 plus p over sigma square.
Okay. Okay.
So here I'm using entropy or inequality.
Hello.
Yes.
Sir, I just got a doubt. I'm not sure like where I'm going wrong. In the
Uh-huh.
entropy power inequality equation, we
Yes.
know that logarithm is an increasing function, right? So if I apply log to the base
Okay.
2 on both sides, then it can be simplified much more, like in a simpler fashion. Like why are we taking it 2 power something and again 2 into like is there any specific reason? Yes, in this if we take log on both sides, so the inequality still
Correct.
holds, right?
Yes, exactly.
Then it
So
is like
so so
h
that is
of
what we're using,
y,
right? So correct. So h of y is greater than or equal to half log 2
h
raised
of
to 2
x.
h of x plus 2 raised to 2 h of z,
Yes, sir.
right? But we can't
Yes,
really
sir. So I
simplify
mean,
this
I was
further,
thinking.
right? Because
Sorry,
this
sir.
is log of something. So this is log of something plus something,
Hmm.
right? So we
That
can't
is
really
sure, sir.
simplify this any further, right?
Not that, sir. In the entropy inequality formula, on the right side, which you have wrote 2 power 2 into h of y is greater than or equal to.
Correct.
So if we take log on both sides, as it is an
Correct.
as a log as is an increasing function, so
Correct.
it will just say that h of y is greater than or equal to h of x plus h of z.
No, no, that's what, right? So it is not greater than or equal
Huh.
to h of x plus
Yes,
h
sir.
of z, because it is
Okay.
log 2 to the 2 h of x plus 2 to the 2 h of z. It's not into over
Can
here,
you
right?
repeat,
There
sir?
was some over here. Hello, can you hear me?
Not over there, sir. On the entropy power inequality formula, I'm saying. So I'm not considering the current question itself.
No, no, that is what. That is what. So if you apply
Yes, sir.
log on both sides,
Yes, sir.
so if you apply log on both sides, you get uh, h of y is greater than or equal to. I'm just applying log on both sides,
Okay.
right? I get 2 h of y is greater than or equal to log of 2 to the
Acha.
2
Sorry, sir.
h of x plus
Oh,
2 to
yes,
the
yes.
2 h of
Okay,
z.
okay. Sorry, sir. I was.
And you can't directly simplify this as h
So
of
yeah,
x plus
my
h of
mistake, sir. Sorry.
yeah, yeah. So that is why it's a little more it's more subtle than that.
Yes, sir. I'm sorry, sir. Like that was my
Yeah.
mistake.
Yes, yes. So it's not saying that h of y is greater than or equal to h of x plus h of z. All right. Any other questions? Okay, so if not, then we meet tomorrow. See you all.
Thank you.